Welcome! In this video, I'll show you how to solve problem 7.2 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now, this problem asks us to use the variational principle to find the best approximation for the ground state energy for the one-dimensional quantum harmonic oscillator using a trial wave function of the form that is shown here, which is some constant a, which will be determined by normalization, over x squared plus b squared, where b, as usual, is an adjustable parameter, which is, remember, just the whole point of the variational principle. Now, how do we go about it? Well, just as a reminder, once again, the variational principle tells us that we can find an approximation for the ground state energy, right? And our approximation will always be at least the same, but probably larger than the ground state energy, and it will be given by the expectation value of the Hamiltonian in this trial wave function state. Okay, so what is the Hamiltonian? Well, we are dealing with the one-dimensional quantum harmonic oscillator, so the Hamiltonian will be minus h bar squared over 2m, right? This is the kinetic part, d squared dx squared, and then plus 1/2 m omega squared x squared. So this is the quantum harmonic oscillator, Hamiltonian. So what we need to do now is, of course, take the expectation value of this. So expectation value for the kinetic part and for the potential. So let's do each one of those. So let's begin, as usual, with the expectation value for the kinetic part. And maybe, actually, before we begin, let's normalize the wave function. So 1 is going to be equal to the integral from minus infinity to infinity of a squared over x squared plus b squared squared. Okay, so, well, we can, of course, pull out the a squared, and then we are left with this ugly looking integral. So how can we solve such an integral? Now, you may have seen something that is kind of like this. There are several different ways, of course, dx, by the way. There are several different ways to solve this. You could try to use complex integration. Maybe you could go for partial fractions. There are several different ways to go about it. Personally, what I like to do is that you see that we have this x squared and b squared in the denominator. So let's take out the b squared so that we are left with x squared divided by b squared in this case, plus 1. So basically something plus 1. That's the whole point. So what I'm going to do here is, well, rewrite everything. So I'm not going to make any major changes here. 1 over, and then we factor out b squared. So we get b squared factor of x squared over b squared plus 1. And all of this is squared. Okay, so we're going to get, and of course dx, by the way. And we still have to square this b squared, so we are going to be left with a squared over b to the fourth. Okay, and then we integrate from minus infinity to infinity, and we have 1 over x squared over b squared plus 1. Okay, and what was the whole point of this? Well, we have something squared plus 1 and dx. And this might ring a bell. If not, don't worry. But the sort of substitution that we like to use here is that we like to say, all right, let's use, maybe let's call it u. So let's say u is going to be b, right? Because there's this b here. So we want to make sure that when we plug in, actually, why did I call it u? Let's just call it x. I'm crazy. Okay, so our x will be b. And again, the whole point is because we're going to square this. So we're going to get b squared, which will cancel out this b right here. And that's nice. That's why we put the b in here. And then we're going to go for tangent of, let's call it u, our new variable. Okay, that is the whole point. And why tangent? Well, there's several reasons. It fits really nicely with our limits in the integral, and also because we are going to be left with tangent squared plus 1. If you can't immediately see it, I mean, the b's cancel out, we get tangent squared plus 1. And that is a very, very nice property, trigonometric identity, and that's going to make things a lot easier. Okay, so that's kind of a standard here. So let's see everything else. So dx is going to be b times the derivative of the tangent, which is secant squared u du. So let's plug it all in. And what are our limits? So at minus infinity, when x is minus infinity, well, if this is minus infinity, what value for u would also go to minus infinity? Well, if you remember the form for the tangent, when it, or maybe it's actually a bit easier if we see it like this, right? Considering that the tangent is sine over cosine. Well, if we want this to be, basically, when does this go to minus infinity? Whenever cosine goes to 0, but from the negative side, right? And when does that happen? Well, at minus pi over 2. And so this part right here is going to be, so the minus infinity will now correspond to minus pi over 2. And similarly, infinity will correspond to pi over 2. You could also have seen these graphically. Maybe that would have been, it depends, you know, how you reason, because the graph is of course something like this. This is, well, this goes through 0, minus pi over 2, and, you know, just a rough sketch, pi over 2. So here it goes to infinity, and here it goes to minus infinity, right? That's why it has those values. So basically, now our new integral, I'm taking my time explaining this because we're going to be using this a lot. So our new integral is going to be as follows. So it's going to go from minus pi over 2 to pi over 2. And then what else? Well, dx is b times secant squared of u du. And then we have x squared over b squared, but x is b tangent u, so the b's cancel out, as I mentioned, and we get tangent squared of u plus 1. Okay, and what is tangent squared of u plus 1? Well, let's do it here, you know, just a quick comment. So tangent is sine over cosine, and all of this is squared, of course, and we are adding 1. So let's take common denominator. So we are adding cosine squared over cosine squared. So we get sine plus cosine, right? So we get 1, right? The sine squared plus cosine squared is 1 over cosine squared of u. So basically, this thing right here is simply 1 over cosine squared of u. Okay. And this, of course, is squared because it was already squared from before, right? This right there. Okay. So let's see. Let's simplify this a little bit. So we get 1 is equal to a squared over b cubed integral from minus pi over 2 to pi over 2. And, well, I simplified this b with this, right? That's why we have b cubed. Then we get secant, but what is the secant? The secant is 1 over cosine squared of u. And this is divided by 1 over cosine squared squared. So we're basically multiplying by cosine to the 4th power, du. So we end up with cosine squared, right? Cosine squared of u. So we have to solve the integral for cosine squared of u. Now, how do we solve that integral? We have seen it plenty of times before. The way I like to solve it is as follows. Okay, so I like to rewrite cosine as 1 plus sine of 2, sorry, not sine, cosine. 1 plus cosine of 2u over 2 du. So that's the way that I like to do it. And, well, now we integrate each one of these. So a squared, b cubed. And the first part is, of course, 1/2. And then u between minus pi over 2 and pi over 2. And the second part is the integral of cosine of 2u over 2. So we get the 1/2 that was already there. Then we get another 1/2. And then we get sine of 2u. And this is, of course, also between minus pi over 2 and pi over 2. Okay, so this is a squared over b cubed. And then we get, well, we can actually factor out 1/2. What else do we have then? Then u between pi over 2 and minus pi over 2. This is pi over 2 minus pi over 2. So we get plus pi over 2. And then we get sine of 2u. But what is this? Sine of 2u. This is going to be sine of 2 times pi over 2. So sine of pi, which is 0. And also sine of minus pi, which is also 0. So then we have plus 0. So this right here is pi, right? Pi over 2 plus pi over 2. So we get a squared times pi divided by 2b cubed. So from this, a squared is going to be 2b cubed over pi. And of course, if you want to find a, you simply take the square root, even though a always or almost always appears squared, so it's kind of unusual to have to use the value of a as is, but you know, just in case, there it is. Okay, so that is the normalization constant. Maybe let's highlight it and keep it close at hand. Now we want to begin with the actual problem. So let's calculate the kinetic energy. Let me maybe get rid of some of these things. All right. So let's begin with the kinetic term. So the kinetic term will require the second derivative, right? Because we will have kinetic term. Of course, as always, you could do everything at once, but you're going to notice that the intervals are very long. It's a lot of work. So doing everything at once just increases the odds of you making some unnecessary mistakes. So I'd recommend that you don't do it. All right, so this would be minus h bar squared over 2m times a squared. I'm just pulling out all of the constants to the front. Integral from minus infinity to infinity of our wave function, right? Which would be 1 over x squared plus b squared. And then comes second derivative of our wave function, dx. So of course, we're going to need to find the second derivative. So let's take a moment to do that. So the second derivative, what is it? Well, let's derive once. So I'm going to write it like this and derive once. So this is basically, at least that's how I like to do it. I write this as x squared plus b squared to the minus 1. So this would be minus, and then we get x squared plus b squared to the minus 2. And then because of the chain rule, we multiply by the derivative of what is inside, which would be 2x. Okay, so that's the first derivative. Now let's derive again. So now we have the product rule. So maybe let's take the minus sign out, and then we derive everything else. So this thing right here would give us minus 2 times x squared plus b squared to the minus 3. And then we multiply by the derivative of what is inside, which is 2x. But there is another 2x here, so this is going to be squared. Okay, and now we need to derive this part. So there, it's going to be plus 2 times, and then x squared plus b squared to the minus 2. Okay, so now let's write this in a little bit prettier. So we get, let's see, this minus sign will cancel out this, so we get 2 times, actually we can also factor out a 2. So, you know, let's take a 2 out. And then we get 4x squared over x squared plus b squared cubed, and then minus x squared plus b squared, and whoops, this isn't, that's my bad. I want to write this in the denominator. So 1 over, and this is squared. Okay, so this is the derivative. So let's write it into our integral. So going back to the integral, we get minus. Now there's this 2 right here, which will cancel out this. So minus h bar squared over m a squared. And now comes integral of minus infinity to infinity. And now keep in mind that we need to multiply this through. So the first part will be 4x squared, but now the denominator is x squared plus b squared, and not cubed anymore, but to the 4th power. And then this part right here is going to be 1 over x squared plus b squared cubed. Okay. So now there's several ways of integrating this. The way that I would go for it is, we have this x squared here, which makes this a little bit annoying. I mean, just in case you want to try any method, this integral is solved exactly as before. So you just have to say, all right, x is going to be b tangent u. And you just plug it in, and then you're going to be left with some power of cosine, and you're going to have to apply trigonometric identities to reduce it until you get only cosines and sines, and then you can integrate it easily. But it is, I think it's a little bit easier if we don't have this x squared up here. I mean, again, it's not like a huge deal. If you don't think of doing this, it doesn't matter. You're going to get to it anyways. But I personally like to do it like this. So what I'm going to do is I'm going to try to, here I'm going to add 4b squared minus 4b squared. That's basically the idea of what we are going to do. Okay? And the whole point of it, again, is just so we can get rid of this x squared in the denominator. Okay? So the first step to simplify this, what I would like to do is just put both of these on the same denominator. So basically, well, the constants stay the same. Integral from minus infinity to infinity, and take common denominator. So this is going to be x squared plus b squared, and this now is going to be to the 4th power. Okay, so we are going to have 4x squared minus x squared, so we get 3x squared. Whoops. So 3x squared minus b squared, and all of this over x squared plus b squared to the 4th power. Okay, and now to get rid of this x squared, what we need is some sort of, because we need it to be of the form x squared plus b squared. So if we were to have 3x squared plus 3b squared, then we could factor out 3, and we could cancel out the x squared plus b squared, and then we have only a second integral that has, sure, b or something, but it's going to be basically the same integral, and that would be very, very nice. So what I'm going to do is I'm going to say, okay, to this, I need to have plus 3b squared and then minus 3b squared, right? Because we can't do anything illegal, we need to subtract the same that we add. So let's now rearrange this. So we get minus h bar squared a squared over m, integral of minus infinity to infinity. And now let's separate this. So we get 3x squared plus 3b squared over x squared plus b squared to the 4th power. And then we get a second integral. And that one is going to have all these remaining b's, which is actually going to be minus 4. So minus 4b squared over x squared plus b squared to the fourth power. Just double checking. Yeah, that's fine. Okay. So now we can, of course, factor out this 3. And now it should be quite apparent that we can just simplify the numerator here. And we get this thing cubed. So we accomplished our goal, which was just getting rid of the x squared in the numerator, which makes the problem a little bit more annoying. Again, it isn't really necessary for you to do this. You could have just went straight ahead here and plugged in x equals b tangent u. I think it involves more work. That's why I just took the time to simplify this a little bit. But again, it really doesn't matter. So if you didn't think of this and you just went straight in, it really does not matter. Okay. So now let's call this I1, and this is going to be I2. Okay, of course, without this 4b squared. It is simply a constant, so it's not going to make any difference in the integral. So what is I1? So I1 is the integral of minus infinity to infinity of 1 over x squared plus b squared cubed. Okay, I did not consider the 3 now. So the result that I get, I need to multiply by 3. Do not forget about it. Dx, of course. So this integral is of the exact same form as the one that we saw when we normalized. So for that reason, we're going to use the exact same trick and see if it works. Maybe it won't. Hopefully it will. So we're going to say x, not u, x. X is going to be b tangent of u, right? For the same reason as before. And dx is going to be the same. So b secant squared of u du. And the limits are also going to go from minus pi over 2 to pi over 2. Exactly the same. Okay, so let's plug it in. So what, this is going to be minus pi over 2 to pi over 2. And then we get, instead of dx, we get b secant squared of u du. And then down here, we need to factor out b squared, right? So we factor it out, and then we need to cube it. So we get 1 over b to the 6th power. And then we have bx squared, which is b tangent of u. So we get tangent squared of u, right? And the b's cancelled out. If you're unsure of this, just watch what we did during the normalization one again. And then we have plus 1 and all of this cubed. Okay. So tangent squared of u plus 1, that is simply 1 over cosine squared as before. So let's take all of our b's out first. Integral from minus pi over 2, pi over 2. And then secant squared is 1 over cosine, right? It's 1 over cosine squared u. And this thing right here is 1 over cosine squared. So we multiply by cosine to the 6th u. Okay? Because again, tangent squared of u plus 1, this is simply 1 over cosine squared. And we need to elevate this to the 3rd power. And then we flip it, right? It's 1 over cosine, and we're dividing by 1 over cosine. So we get, right? It goes up. Okay, so in the end, this is going to be cosine to the 4th power. Okay, so we now need to solve that integral. So this is a sort of integral that we'll encounter very often. Again, there's probably several ways to deal with it. I'm going to do exactly what we did before. So we know that cosine squared, maybe I'll write it here, cosine squared of u, this is simply 1 plus cosine of 2u over 2. So let's use this. So this is going to be 1 over b to the 5th. So 1 over b to the 5th. And then we get integral from minus pi over 2 to pi over 2. And then we have 1 plus cosine of 2u over 2. And this thing squared du. Okay, so this now let's just multiply through. So this 1/2 will be 1/4, and we can pull it out. So we get 1/4b to the 5th, blah, 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 and pi over 2. Okay, so now we get 1 plus 2 times cosine of 2u plus cosine squared of 2u du. And what is the integral of cosine of 2u? We already solved this. I think I deleted it, but you can rewind if you want to the normalization part, because we get sine of 2u. And we are integrating from minus pi over 2 to pi over 2. So we are going to get sine of pi minus sine of pi. Both of them are 0. And this is very important. Every cosine integral that we do is going to be 0. All right? So I hope that this is very, very, very clear. Maybe I'll just show you one more time. So we're integrating cosine of 2u from minus pi over 2 to pi over 2. This is, of course, sine of 2u between minus pi over 2 and pi over 2. So this is sine of pi, which is 0, minus sine of minus pi, which is also 0. Right? So that part is 0. And what is this cosine squared of 2u? Well, there we will use the exact same thing. Again, this formula right here. So we have 1/4b to the 5th, integral from minus pi over 2 to pi over 2, and then 1 plus. And now instead of cosine squared, we write 1 plus cosine of 2 times 2u. So we get 4u over 2. And again, cosine of 4u, it's going to give us sine of 4u when we integrate. So we're going to get sine of 2 pi, which is 0, and minus sine of minus 2 pi, which is also 0. So again, the cosine part will simply be 0. So we're going to be left with the integral 1/4b to the 5th and integral from minus pi over 2 to pi over 2 of 3/2. Okay, so 1/4b to the 5th times 3/2 times, and then we get pi over 2 minus pi over 2. They add up. So plus pi, basically. So we get 3 pi over 8b to the 5th. I mean, I don't know why I wrote it like this. We have to plug it in. We're not done yet. Where did this come from? All right, here. So this is where we have to plug it in. What was the result again? So 3 pi 8b to the 5th. So maybe I'm going to put it as a comment here. I1, this is 3 pi 8b to the 5th. Okay, so that is our result number 1. Now let me get rid of all this and let's go for the next integral, which will be done in very much the same way. It's going to be the same procedure, right? Because the integral is very, very similar. Okay, so in this integral, so I2, this is going to be integral from minus infinity to infinity of, well, maybe I'm going to write it as dx. So dx x squared plus b squared to the 4th power. Okay, so how do we solve this? Well, again, let's use x is equal to b tangent of the, tangent of u, and then dx is going to be b secant squared of u du. And yeah, now let's plug it in. Again, limits are going to be the same as before, from minus pi over 2 to pi over 2. So minus pi over 2 to pi over 2. So this is going to be b secant squared of u du divided by, and again, we have to factor out b squared. And when we factor it out, it's going to get elevated to the 4th power. So we get 1 over b to the 8th. And then we get, it's going to be tangent squared of u plus 1 to the 4th power. Again, this is going to be cosine squared as before, but let's go one step at a time. So we are going to get 1 over b to the 7th when we consider this b. Integral of minus pi over 2 to pi over 2. And secant squared is 1 over cosine squared of u. Tangent u plus 1, as we mentioned, that's also secant squared, so we get 1 over cosine squared. That thing is to the 4th, so we get 1 over cosine to the 8th. And then we have to flip it, right, because we are dividing by that. So we get cosine to the 8th u du. Okay, so this whole thing is going to be cosine to the 6th power. And as you can see, it is of the same form as before. Okay, how do we solve an integral of cosine to the 6th? Well, again, what I would do is use our beloved formula that cosine squared of u is 1 plus cosine of 2u over 2. And then we can just write this as cosine squared cubed, right? So cosine squared, and that is cubed. So by doing that, we can now rewrite cosine squared with this formula. So we get 1 plus cosine of 2u over 2 cubed du. The 1/2 we can of course pull out of the integral, and it's going to be 1/2 cubed. So we get 1 over 8 b to the 7th power. And then the integral is going to still be there. And then we're just going to expand the integral. So what is it going to be? It's going to be 1 plus cosine of 2u cubed. So, you know, it's just your binomial cubed. So it's going to be 1 plus 3 cosine of 2u plus 3, cosine squared of 2u, and then plus cosine cubed of 2u du. Okay, so let's go step by step. So this thing right here is 0. Again, we are integrating cosine of 2u. We have done that a few times already. I showed you why it is. If you joined the video later, you can go back either to the normalization section or the one just after this, where I explain it. Then, what else do we have? Well, let's take it here, minus pi over 2, pi over 2. And, well, it's going to be 1 plus, and this cosine squared of 2u, let's rewrite it. So we get 3 times 1 plus cosine of 2u over 2. And again, this part is 0. So we are only left with the 1/2. And then we have the cosine cubed. Cosine cubed is cosine times cosine squared. I mean, I guess there's several ways to do it. I think I'm going to do it like this. I'm going to write it cosine cubed of 2u, and I'm going to solve it separately. Okay? So maybe I'm going to call it I3 and just solve it here quickly. So integral from minus pi over 2 to pi over 2 of cosine cubed of 2u du. Okay, so how do we solve an integral like this? Okay, so now we could do the same thing, right? Using that formula for cosine squared is, you know, blah, blah, blah. But I personally think that it's a bit better and a bit easier to write this as cosine of 2u times, again, cosine squared, but this time use a different formula. Use 1 minus sine squared of 2u, and of course the u. And the whole point is that now we get, well, integral blah, 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 the same thing. The first term will be cosine of 2u, but we have seen many times this is going to be 0. And then the second one will be minus sine squared of 2u cosine of 2u du. So we have sine squared cosine 2u. So this is an easy integral. We have seen it a lot of times before. We solve it by substitution. We say, all right, t is going to be sine of 2u, and thus dt is going to be cosine of 2u times 2, of course. So du, so cosine 2u du we already have. We're going to have to divide by 2 so that we have the exact same thing in our integral. So we can now rewrite the integral as going, and let's see, how do our limits change? So when it is minus pi over 2, we plug it in here, so it's going to be pi, so we get 0, and then our upper limit is going to be also 0. All right, so we are integrating from 0 to 0, so not really much point in doing much else. If we're integrating from 0 to 0, right? We're not integrating anything. Just double checking. So pi over 2 times 2, we get pi, sine of pi is 0, and same there. All right. So that was quite nice. So this particular integral, cosine cubed, is 0. So let me get rid of this. I mean, you could also have gone ahead and found explicitly that it is 0, but it is just what integrals are. I mean, if you're integrating, if you're not moving, then you're not going to have any area, right? Okay, so du. So in the end, our integral right here is 1 over 8 b to the 7th, integral of minus pi over 2 times pi over 2, and then we have 1 plus 3 halves, which is 5 halves. So we get 5 halves times 8, whoop, that's dividing, sorry, 1 over 8 b to the 7th times pi, right, which comes from integrating just 1. We have done that a few times already. Okay, so basically this is 5 pi 16 b to the 7th. So let's now plug it in right here. Whoops, there we go. So maybe let's get rid of this. So the integral that we had was minus h bar squared a squared m, and then we have 3 times, so 3 times our previous result, so 3 times pi over 8 b to the 5th, and then we have minus 4b squared times our newest result, which is 5 pi 16, sorry. So 5 pi 16b to the 7th. So let's see, we can factor out pi and b to the 5th. We can see that this cancels out this partially, this cancels out this partially. So we can do minus h bar squared a squared m times pi over b to the 5th. And we are left with, let's see, so 9 over 8 minus, and then we have 5 over 4. So I guess we can rewrite this as 10 over 8. So minus 10 over 8. That does not look like a 10. So 9 minus 10, this is minus 1 over 8. Now I'm going to make some more room down here. Now that we already used the result, it doesn't matter. We can just get rid of it. You can always rewind if you want to look at it again. Or if you want to look at it again. So this minus sign would cancel out this. So we get h bar squared over m pi b to the 5th times 1 over 8. And now we plug in the value for a squared, which I don't remember. Where is it? There. A squared is 2b cubed over pi. So 2b cubed over pi. So the pi's cancel out. We get h bar squared over, let's see, it's going to be m b squared and a 4. So this is the kinetic contribution. It was quite a bit of work, but we got it. And the thing is that now that we learned to do those integrals, the rest is going to be, much, much, much easier. I'm going to highlight it. And now let's take it away so we can make some more room for the rest of our annotations. Okay, so now let's go and work with the potential. So what is the expectation value of the potential? So this is going to be 1/2 m omega squared a squared, right? All the constants come out. Integral of -infinity to infinity. What else do we have? And then we have our wave function, of course, which is going to be squared. So we get 1 over x squared plus b squared squared. And we still have our x squared. Okay, so how do we integrate this? Well, this is basically the same that we have been doing. So again, let's say x is going to be tangent b times tangent of u. Thus, dx is going to be b secant squared of u du, the same as before. And again, the limits of the integral will also be the same. So from minus pi over 2 to pi over 2. Minus pi over 2 to pi over 2. If you just joined and you don't know where these limits came from, go back to the normalization part where I explained this thoroughly. Okay, so x squared is going to be b squared tangent squared of u. Then we get times b secant squared of u du. And then we divide by, and here we get, again, we have to factor out b squared squared. So we get b to the 4th power. And then we get tangent squared of u plus 1 squared, which means secant squared squared. So basically secant to the 4th power, which is of course 1 over cosine to the 4th power. So basically we multiply by cosine to the 4th power. The du is already there, never mind. Okay, so now we can simplify a little bit. We know that secant squared is 1 over cosine squared, and tangent squared also has 1 over cosine squared. So it's going to simplify a lot, actually. Minus pi over 2, pi over 2. And, we can actually, it's going to be just b because we get b to the 4th, but then we have b squared and b. So we get just 1b. And then we are left with only sine squared of u inside, because the cosine to the 4th cancels out with this and with the cosine part of the tangent. Okay. So what next? So now we have to integrate this thing right here, the sine squared. And this is going to be exactly the same as when we integrated the cosine squared, except for the minus sign, right? Because this is going to be, because sine squared of u, that is simply 1 minus cosine of 2u. This is an incredibly important identity, as you can see. Now, the cosine integral is 0, as we have seen so often already. So this integral will simply be 1/2, which we can pull out. So we get 1/4 m omega squared a squared b. And then we multiply by pi, because this integral will be left simply integral of du. So we get u evaluated at pi over 2 minus pi over 2. So we get pi, as we have seen so many times. So now let's plug in the value for a squared, which I already forgot, so I need to double check. It's 2b cubed over pi. So 2b cubed over pi. So pi's cancel out. This cancels out this at least a little bit. So we get m omega squared b squared. And there's a 2 downstairs, right? Because this canceled out part of this. Yeah, okay, there we go. So now we have to put all of it together. So let's see, the expectation value for the Hamiltonian will be the sum of both of these. So h bar squared over 4mb squared plus m omega squared b squared over 2. And this is, of course, the energy, right? The expectation value of the Hamiltonian is the energy. So if we want to minimize this with respect to our parameter, we are going to derive and set it equal to 0. So deriving this first part, let's see, h bar squared for m, and then we have b to the minus 2. So we get minus 2b to the minus 3. And then let's see, plus m omega squared, and then we get 2b. The 2 cancel out, and we get another b here. Okay. So let's see. Now, this would be h bar squared over 2m b cubed. This is equal to m omega squared b. Okay, so b of course can't be 0. Let's multiply by b cubed. Whoops, a little bit too much. So h bar squared divided by 2m squared omega squared. This is equal to b to the 4th power. And well, of course, that means that b is going to be h bar squared 2m squared omega squared to the 1/4 power. Okay, so let's plug this into our formula for the energy, and let's see how good or bad of an approximation it is. So let's see. So that's our energy. Maybe we're just going to say E. But our minimal energy that we can find with this wave function is h bar squared over 4m times b squared. So we're 1 over b squared. So we get 2m squared omega squared h bar squared to the 1/2 power, and then plus m omega squared over 2 and h bar squared 2m squared omega squared and 1/2. Okay, so now let's simplify this a little bit. So let's see. So this here is basically h bar, m, and omega, right? There's no squares. So we get h bar here. And then we have square root of 2. We have a square root of 2 upstairs, but we have a 4 down here, which is basically 2 squared. So we basically have 2 to the 3/2 power. Then we have m, which cancels out with this, and omega, which stays there. And then we have here, let's see, the m cancels out. This omega cancels out the exponent, so we get h bar omega divided by 2 to the 3/2 power. So this is basically h bar omega over 2 to the 3/2 power times 2, right? Because it's the same, so yeah, times 2, which is basically 2 to the 1. So we can simplify this further as h bar omega divided by 2, or basically square root of 2. I was going to say 2 to the 1/2, but square root of 2, which is relatively close to the ground state of the harmonic oscillator, right? The ground state energy for the harmonic oscillator we know is h bar omega over 2. And this is relatively close. So, you know, pretty decent, and we didn't have to solve the entirety of the Schrödinger equation for the harmonic oscillator, which, if you saw the first part of the course, you know, is pretty annoying. So yeah, you can see that the variational principle is the same always. I mean, we just start out with this, we write out the Hamiltonian, we calculate the expectation values for the kinetic and potential terms. And sure, the integrals can be annoying, but it's very straightforward. And then once we have the energy, we just minimize, set it equal to 0, find the value for b, plug it in, and that's it. And yeah, it's pretty simple. So if this was useful to you, please make sure to, you know, leave a like on the video, comment, subscribe, and maybe share with your classmates if you think they could benefit from this as well. I'll see you in the next video. Thank you very much for watching.